All right, cool. Well, welcome to your last CSE215 class. So this is the last course, last meeting of the quarter. Um, and I just want to say good job, everybody. All six of you that made it to the end, I guess. Yep. So yeah, hopefully this course has been interesting and or useful to you. Um, I think you'll find that a lot of the topics we touched on in here come up in later courses, um, and that'll only help you down the road, right? So you know. We try to talk about some interesting things in here. Try to make these subjects interesting. So yeah, if you enjoyed it, that's great. That's totally awesome. Um, and all of the stuff we've been talking about, is sort of foundational to computer science at large. It's a lot of the stuff that kind of underpins the things we do, even if we don't think about, mathematical induction when we're writing a recursive function for searching trees, for example. All that stuff is in there, so it all kind of ties together, and it's part of a bigger picture which continually forms the more you do this. So so your final exam is on Monday. It's at 12 o'clock. So even though class starts at 12:30, your exam actually starts at 12. Okay, so make sure you show up at 12. Take advantage of that extra half hour. It's an hour and 50 minutes for the exam, and it will be the same structure as the midterm. So I'll post an assignment on Canvas, which will open at 12 o'clock on Monday. Um, and it'll be basically a PDF you can download that'll have your questions in it. And then I'm going to ask you to either write up by hand or type in your answers, submit that as a PDF through Canvas. So yeah, if you're in the A section of 222, this comes right after 222. And then you're done with your CS exams. So kind of gets it all over with at once. But yeah, it can be a bit of a long morning that way. If you have any doubts about being able to type up your answers, you're welcome to write them neatly. The only thing I ask is, try to organize your work so that as I read from the top of the page to the bottom, I can follow what you're doing. And try to make your marks on paper something that's easy to see after you scan it. So I recommend, a soft pencil, like a number 2 pencil, so that you can, erase and make corrections and so on. And I don't have to, break out the interrogation light to read what you wrote. Um, um, and yeah, if you have if you have accommodations regarding extended test time and stuff, that automatically happens, right? So the exam does not lock out at 150. It stays open on Canvas, but there's some kind of horrible penalty I'll put on, like 10 minutes per minute, 10 points per minute, I think. So you have to keep track of time, and I'll remind you in Zoom when the deadline is coming up. But make sure you submit by the deadline. And if you have, arrangements to have more time, right, that's automatically taken care of. It's encouraged that you write it out on paper. I think that works better than trying to type it, just because there's so many weird symbols. There's backwards E's and things like that. And trying to invent an alphabet that lets you type those things, and then you have to give me a key and all of that. It's just a lot harder. So yeah, write it up on paper by hand. I think that's your best bet. But if you're very fluent with typesetting on the computer, you're welcome to do that. Um, it's probably a 100-point exam, but you can look in Canvas to see what the percentage is towards your final grade. And it's probably 20 or 25%. I don't remember what I set it up to, but that's listed in Canvas in the syllabus, or in the additional course info. 40%, wow, that's heavy. So the final exam is cumulative. It goes back to, the beginning when we started talking about set theory. But, more emphasis on the stuff we've done since the midterm, since that hasn't been tested yet. And yeah, on Canvas it'll show up as 0 points right now because the exam hasn't been written or posted there. But it'll probably be 100 points. But whatever the number of points, I mean, I could make it a 1,000-point exam, but then each question would be worth 100 points. So that would be kind of fun. And let's see. So, oh, that's the wrong course, isn't it? We don't want to do 222 in here.
Because that would confuse us unnecessarily, and that would not be good, would it?
Yeah, definitely. Yeah, it says the final is due at 12. That's when the final starts, and it won't actually have a due time on it because, like I say, it doesn't close down automatically. So if something happens and you turn it in a minute late, it will still accept that submission, but then I'll take off points once I'm grading it. Nope, the final starts at 12, so it's 12 o'clock to 1:50. So if you look at the Clark exam schedule, classes that start at 12 or 12:30, the final exam starts at 12. So make sure you get that extra half hour. High noon. It is. All right, so this was the study guide I posted a few days ago. And we can just go through this if we want, but again, if there's any particular questions, we can start with those to make sure that we get to them.
Could you go over power sets again?
Go over which one? Power sets?
Yeah.
Sure. So if you have a set right, there's a set of three things, A, 1, and triangle, right? So the power set of S is itself a set, and the elements of that set are the subsets of S. So what are all the subsets? Well, there's the singleton set containing A, the singleton containing 1, the singleton containing triangle. There's a few sets that contain 2 elements. There's the set S itself, because the set is always a subset of itself, and there's the empty set. So the power set contains 8 elements, and each of those elements is a set. So it's a set of sets. And if I ask you to make the power set of a set, you can always do a check on the number of elements. And a power set is just 2 raised to the number of elements in S, as long as that's a finite number. All right, other questions? It's not exactly every combination of elements. It's a collection of sets. So power set is just another set. In this case, it's a set that has 8 things in it. And each of those things is a set. And if we looked at all of those sets, we could say in some way, you know, that's the collection of all different combinations of elements from the set S. But you got to be a little careful with the terminology, right? Because every combination of elements, so any combination of elements will comprise the elements of one set in the power set. We can say that and have it be correct. But if you're thinking for a quick way to generate the power set, yeah, just take all the combinations of this and put each one in a set. Quick 40,000 foot overview of the Pigeonhole Principle and application to counting problems. Absolutely. Pigeonhole Principle basically relates to putting things into buckets. You have a set of containers and a set of things, and you're going to put things into containers. And the question is it possible to do this without doubling up? Without ending up with two things in one container? And that's effectively what the Pigeonhole Principle deals with. Yeah, we can say cardinality for the number of things in a set. Cool. So, suppose you have k containers, and suppose you have k plus 1 objects. So if we start putting these objects into containers, the Pigeonhole Principle, all it says is at least one of these is going to end up with two or more things in it. And it's basically a counting argument. If we had k objects, we could put one in each container and there'd be nothing doubled up anywhere. But if we have more than k objects, we're going to have to double up somewhere. Okay, that's kind of the hand-wavy description of the Pigeonhole Principle. And we can use it for different counting arguments, such as, for example, what's the largest set of numbers, set of integers, such that no two have the same last digit. So what's the size of the largest set of integers you can construct such that no two integers in that set have the same last digit? And we can use the Pigeonhole Principle for this. We could make 10 containers, and we put our numbers from our set into containers based on their last digit. So if the last digit is a 0, we'll put it in here. If it's a 1, we'll put it in here. If it's a 9, we'll put it in here. And we know that if we have 10 numbers, right, they could all end with the same last digit. We can imagine if we had 1,000 numbers, some of them are going to have the same last digit. So the Pigeonhole Principle says if we have k plus 1 objects, then at least one of these containers will have two things in it. If we have k plus 1 numbers, at least one of these containers will have two things in it, two numbers, which means those two numbers have the same last digit. So if we have k plus 1 objects, we're not going to have all of our numbers having a unique last digit. But if we have k numbers, or 10 in this case because we have 10 buckets, then it's possible each number would have the same last digit. And so a lot of times we ask questions like, what's the smallest k such that, or what's the smallest number such that this is bigger than k? So that's an example. How many people can you put in a room such that no one has the same first initial? 26 letters in the alphabet, 26 buckets or containers. If we have 27 people, then at least 2 of them are going to be in the same container, so they have the same first initial. So you can put 26 people in a room and possibly have unique initials. When you get to 27, you're guaranteed at least 2 people have the same initial. Does that make sense? Cool, you're welcome. Okay, good. Grammars and languages. So this was our last topic. And so we haven't done a homework on it. So I would like you to understand the notion of a phrase structure grammar. And I'd like you to do be able to analyze a phrase structure grammar and be able to put one together. So right, we've got the vocabulary, the terminal symbols, the start symbol, and the production rules. So if I gave you a language where I told you what was in these sets, I could say which of these strings belong to the language. And your goal would be to start from the start symbol, apply production rules, and see if you can get to the string that I'm asking you about. Sure. So let's do vocabulary equals 0, 1, A, B, and S. Terminal symbols will be 0, 1. Start symbol will be S, and our production rules will be S goes to A, S goes to 1A, S goes to 0B, A goes to 10B, B goes to 001, B, or B goes to 111. I don't know if this is a valid grammar or not. I'm making this up. My invisible hands, thank you. Alright, so I'm just making this up. I don't know if this is a reasonable language or not. But 0, 1, A, B, S, terminal symbols are 0, 1. And here's our set of production rules. So let's say I asked you to show me some strings that belong to this language, the language generated by this. So our start symbol is S, and we could replace S with a 1A, and we can replace A, looks like the only thing we can replace A with is 10B. So 1A is part of our language, which means 110B is part of our language. And B could be a 111. So 110, 111, that's definitely part of our language. But B could also be replaced with 001B. And since B could be 111, this means 110, 001, 111. That's also part of our language. Or I could have said, my start symbol could just be a 0B, and B could be a 111, so 0, 111. That's part of my language too. So I could ask you to produce strings that belong to the language, or I could give you a string, like, like this, and ask you, is that part of the language? And so, well, it's either got to be an A, or it's got to be a 1 followed by an A, which it can't be, or a 0 followed by a B. If it's an A, it's got to be a 1, 0 followed by a B, which it's not, but maybe it's a 0 followed by a B. So maybe this is a 0 and this is a B. And then you can see, oh yeah, B could be a 001, which is a B followed by a 111. So yeah, that's part of the language. All right, makes sense? Yes, you can use your notes. You can use your textbook. You can use, your homeworks if that's part of your notes and so on. But don't use any online resources unless, if you've got your homeworks on Dropbox or something, right? But don't go to Stack Overflow. Don't go to Chegg, things like that. What else about? Yeah, class videos are okay, but even with tags on the videos, hour 50 minutes is not a lot of time. So you definitely don't want to spend, a good chunk of your exam time trying to get through the class videos. Um, but if there's something there that you really think will help, yeah, that's fair game. Finite state machines, we touched on briefly. Looking at state diagrams, we did one example of that. Turing machines, I may ask you to analyze a Turing machine. I won't ask you to come up with a Turing machine, but I could give you a Turing machine with a set of state transitions listed, and then ask you, what does this do if your input tape looks like this? I won't ask you about NP completeness. I won't ask you about P problems, non-deterministic Turing machines, stuff like that. So pretty high level topics here. Mm-hmm. Yeah, sample Turing machine question. So suppose your initial state is S0. So there's a set of state transitions, and let's suppose your tape initially looks like this. And you're originally sitting right in front of that first letter A. And I could say, show me what this program does to that tape. And so we're starting in S0, and the question is, can we find a state that says S0 and says the current letter is A, and this first state happens to match that. So this says write an A into that position on the tape so it doesn't change anything. Move left, so we move over to here, and go to S state S0. So now we're in state S0 and there's an A, and we check our set of instructions, and S0A, yep, that's this instruction again, so it says write an A, so that doesn't change. Move left, so we go here and go to state S0. Same thing, S0 and there's an A, still that first instruction, so it says write an A, move left, and go to state S0. So now we're in state S0 and there's a B. So this doesn't work, but this does, state S0 and a B. So it says write a B, go to the left, and stay in state S1. So now we're in S1 and there's an A, no, 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 yes, there's S1 and an A. And so it says write a B, so this will change to a B. and move left and stay in state S1. So here's an S1 and a B, no, no, yes, right there. It says write an A and move left. And now we're in state S1 and there's a C. So no, 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 yes, there's our state S1 with a C. It says change that to an X, move right, and go to state S2. So we're in S2 and there's an A, and there's no state that says S2 with an A, so our machine halts. And so your output would be X, A, B, B, A, and your read write head is sitting right there. Cool. There's a bunch of these in the textbook. A bunch of examples of machines and inputs, and you're asked to evaluate the output. And remember, half the questions in the book have answers in the back. So you're welcome to look at those to get some practice on this. The only thing is, sometimes this left means move the arrow left. Sometimes we think of the left as saying move the tape left, which would move the arrow to the right. So it may be backwards from this, depending on where you're looking. But the concept is exactly the same. Cool. Let's see, is graph theory going to be big on it? There will almost certainly be a graph theory question. And let's see what I posted. So when we do Turing machines, if I say left, that means move the arrow to the left. But if you try to do the problems in the book and it looks like you're getting the wrong answer, check the book and see what it's doing, because the book may be moving the tape. But if I ask you to do a Turing machine question, when we say left, that's the arrow moving left, or the read write head moving left. So graph theory, so kind of like the homework that you did most recently, right? Basic concepts of a graph, edges, vertices, being able to make a matrix corresponding to a graph, being able to make a graph from a given matrix, knowing what an Euler path is, where you travel along each edge once, knowing a Hamilton path, where you hit each vertex once, being able to identify a Hamilton path or an Euler path, or circuits in a given graph, the concept of isomorphism of graphs. So, I mean, this is a straight hit list from the homework, right? And Dijkstra's algorithm, definitely know how to do Dijkstra's shortest path algorithm to find the shortest path through a weighted graph. Good, these are good questions. Well, we can continue working backwards through here. Yeah, keep them coming. The more recent stuff is untested from the midterm, so let's just keep working backwards since we've already done grammars and graph theory. And Pigeonhole, let's talk about the other parts of counting, which is combinations, permutations, product rule, and so on. Definitely understand the product rule, which lets us break a task into a succession of tasks, and the sum rule, which lets us break a task into a choice of, doing one of multiple subtasks, where you can do this or that, so soup or salad, as opposed to choose an entree and a dessert. Yeah, we can do recursion, definitely. Permutations and combinations. So permutations are ordered, combinations are unordered. Okay, definitely keep that straight. Put it on your notes, highlight it, right? Combinations are not ordered, permutations are. And when you see a question involving combinations or permutations, it's helpful to use these symbols in developing your answer, right? The worst choice for answering a question like this is just to write down a number. Because if one digit is off, right, I don't know what you did. If you've got the right number written down, I'm pretty certain that you probably did the right thing. But if the number is wrong, if you made a mistake in your calculation, was it a big mistake or a small mistake? There's no way to know. So if I say, 20 people whose names come from an alphabet of 10 characters go to a restaurant where there's 5 entrees and 17 desserts, how many different ways could people order? I wouldn't do that. I don't even know what the answer to that is. But if I do that, what you'd like to do is write your answer in terms of permutations, combinations, products of things, sums of things, plus and minus, right? But show me what you're doing to get to your final answer, right? And then once you've got it written in these terms, right, you can do, n factorial over n minus r factorial, right, where you'd have numbers instead of n and r. But, write it out in terms of the things that you're going to actually calculate. And if you take it this far, you're probably good. Don't spend a lot of time. If it's a simple number, 2 times 3, go ahead and write down 6. But if it's a bunch of complex calculations and all I see is this, if this is correct, you'll get credit for it. Okay? If you want to take it out to a number, that's fine. And if your number is wrong, but this is correct, you'll still get credit for it. Okay, but I got to be able to see, that you went with one of these and you got to these formulas. And that's the goal, is seeing that you know how to apply these different counting mechanics. And Pascal's triangle, the only thing to know there is that, each element in the triangle corresponds to a combination. Based on the row and column. And binomial theorem, a plus b to the n, the coefficients come from Pascal's triangle. They're just combinations. Sorry, I'm finishing my lunch here while we talk. What else on product rule, sum rule? Principle of inclusion, exclusion, that's where you add and then subtract. Alright, and this is like that number of students who swim or play tennis question on the homework, which I think everybody got perfect. So that's probably fair game for the exam. So the number of things in a union is the number of things in each set minus the number of overlaps. So that's inclusion, exclusion. Alright, let's see what else. Recursive functions. Yeah, so someone asked about recursion and such. So recursive functions, and basically a recursive function is a function where you describe the value of the function in terms of other values of the function. So a classic example might be something like, let f of n equal 1 plus 2 plus n. So the sum of the first n integers, that's what our function f is. And we can write it like this. We could also write it as the sum from I equals 1 to n of I. But we can also define f in terms of f by doing the following. We could say f of n equals n plus f of n minus 1. So this is the sum of the numbers 1 through n minus 1, and if we add n, we've got the sum of the numbers from 1 through n. That's f of n. Usually when you do this, you need some kind of base case. Because if I use this to try to find f of 1, all it's going to tell me is f of 1 is 1 plus f of 0. And f of 0 is 0 plus f of minus 1, and f of minus 1 is minus 1 plus f of minus 2. And I can keep doing that, but I'm never going to get to an actual number which tells me what any of these things are equal to. And my quest to write down f of 1 will never come to an end. I'll be writing these things forever and ever and just going deeper and deeper, right? This is what blows up your computer stack. If you ask a computer to do this, it doesn't do it forever. It does it till it runs out of memory, and then it says stack overflow or seg fault. So we put in a base case where we say something like 0 if n equals 0, n plus f of n minus 1 if n is bigger than or equal to 1. Where we understand n can't be negative. So now if I want to find f of 1, it's 1 plus f of 0. F of 0 is 0. So f of 1 is 1 plus 0 is 1. And now we can bootstrap from there and find f of any positive number. So that's an example of a recursive function. It's related to induction because if we wanted to prove that this always gave us the sum of the first n integers, we could make an inductive argument. We'd make a proposition that f of n equals the sum of the first n integers. We have to prove f of 0 is true, or p of 0 is true, which is f of 0 is correct, which is true because of the base case. And if we assume f of n is the first n integers added together, we can easily show f of n plus 1 will also be the sum of the first n plus 1, because we get to assume that, f of n is correct. So recursive functions, mathematical induction, closely related to each other. Yeah, the pain goes away eventually, and actually turns into a bit of pleasure. It actually becomes really satisfying to picture a problem as a recursive algorithm and then code that up. That actually starts to feel more natural at some point for most people. But in the beginning, it's just kind of, it does hurt your brain because our brains don't seem to be wired for that. And I don't know exactly what that means because we do very well with stacks. That's kind of seems to be inherent to our processing. I don't know if that's social conditioning or hardwiring. But recursion, I think because when we try to solve a problem, we're taught, that we can't use, you can't use a word to define the word. Like, what is cheese? Well, it's a food that tastes like cheese. That's not a good definition of cheese, right? So we kind of learn not to think that way. But that would be a recursive definition. But we'd need a base case, right? So I don't know what the recursive definition of cheese is. Maybe that'll be an exam question. That's if mean teacher shows up. All right, cool. What?
Will we become an exam question if evil teacher comes up or shows up?
I could ask you to write a recursive definition of cheese. Evil teacher doesn't actually write your exams, though. Evil teacher is like a Saturday Night Live character. Let's see. All right, so mathematical induction, which we were just talking about. So yeah, you'll definitely see, probably one proof involving mathematical induction. So basic setup, our goal is to prove some family of propositions, say p of n for all n bigger than or equal to 1. Okay? And if you're asked to prove something, prove that the sun is warm, right? we can't start talking about P of n, P of 1, that kind of thing until we define what P is. So your first challenge in an induction proof is to take what you're asked to show and put it into a framework where it works with mathematical induction, which usually means somehow describing it as trying to prove that a family of propositions is true. Okay, so that's kind of your first step, and at the end of that, you need to state, right, for the person reading your proof, what this family of propositions is. What does P of n say? And so, you say something like, let P of n be the proposition and then you spell out what that proposition is. All right, and then prove that P of n is true for all n bigger than or equal to 1. So to use mathematical induction to do this, we do two things. The first is called the base case. And the goal of the base case is to prove, say, P of 1, P of whatever the smallest value of n is typically. And this we can do if we've defined what P of n is, we can write down what P of 1 is, and then just demonstrate that that's true. Right? And you can always prove that a particular proposition is true if you can, break that proposition down into things that you know are true. The problem is we can't prove, P of n for all n unless we were to actually write out, for all possible n what each of those propositions is and show that it's true. If P of n is the proposition that, the sum of the first n integers is equal to n times n plus 1 over 2. Well, I can show that for any particular n, but our goal is to prove it for all n. So we do a base case first. Yeah, we can make this less generic. So let P of n be the proposition. Let's say sum from I equals 1 to n of I is equal to n times n plus 1 over 2. We've seen this one before. So proposition that the sum of the first n integers is this formula. All right, so we want to show that this is true for all n, so I form it as a proposition. Let P of n be the proposition that this is true. So P of 1 is one proposition. It says the sum of the first one integers is 1 times 2 over 2. P of 2 is another proposition. Says the sum of the first two integers is 2 times 3 over 2. Right? So each of those P sub n, P parentheses n, is one proposition. The problem is there's an infinite number of n bigger than or equal to 1, so there's an infinite number of propositions. And we can't prove each of those one by one, so we use induction. So first we want a base case. Since we're trying to show this for all n bigger than or equal to 1, let's prove that P of 1 is true. So prove P of 1 is true. Now usually if you just say prove P of 1, it means prove it's true. Okay, so what does P of 1 say? Says P of 1 says sum from I equals 1 to 1 of I is equal to 1 times 1 plus 1 over 2. And there's really not a whole lot of work to do here. Usually the base case is writing this out and saying, this is just, 1, and this is 1 times 2 over 2, and those are both equal. Right, so I figured what the left side was and what the right side was, and I stated that those were equal, and so P of 1 is true. Or sometimes, you could do this. All right, so the base case is usually not the trick. So the trickier part is the inductive step. which says if n is some number bigger than or equal to 1, and we assume p of n is true, prove that p of n plus 1 is also true. All right, so we get to assume this is true, and we have to show that's true. If we can accomplish that, then we've proven this statement, and that, together with the base case and mathematical induction, will tell us p of n is always true. Okay, so how do we do this proof? So proofs, we're going to number our steps, we're going to write down something that is true, and we're going to explain why it's true. So statement 1, p of n. Why is p of n true? That's the hypothesis. Saying prove this means if I assume this is true, can I show that's true? And our proof is, okay, we're going to assume this is true, we're going to, apply some logic and spin in a circle 3 times, and we're going to end up with p of n plus 1 is true. So we start with a hypothesis, p of n. P of n, there's nothing we can do with that. It's 4 characters, right? So we need to turn this into something that we can do something with. So let's use the definition of p of n. What does p of n say? It's the proposition that this is equal to that. Since we're assuming p of n is true, we can now say the sum from I equals 1 to n of I is equal to this. And the reason is that's the definition of p of n. Now you write this out, you go on the side in your ignore section, you scratch your head, you write down what p of n plus 1 is, you stare at it, you do whatever it takes, and you get this idea, hey, let's add n plus 1 to both sides of this. Since I know this is equal to that, I can add the same thing to both sides, and the results will still be equal. So now I'm going to say sum from I equals 1 to n of I plus n plus 1 equals n times n plus 1 over 2 plus n plus 1. And the reason for this is algebra adding n plus 1 to both sides of an equality. But if it's clear that's what you did, you can just say algebra. That's fine. All right, so now starting with p of n, we've proven that this is true. And this I can rewrite as the sum from I equals 1 to n plus 1 of I. And why is this equal to the sum from 1 to n plus 1? That's just, properties of summations. So this says take the sum of the first n integers, and this is the n plus first integer. If you add those together, that's the sum of the first n plus 1 integers. And now I'm going to go algebra crazy on this right-hand side and say this is n squared plus n over 2 plus 2 times n plus 1 over 2, which is equal to n squared plus n plus 2n plus 2 divided by 2, which is equal to n squared plus 3n plus 2 divided by 2, which is equal to n plus 2 times n plus 1 divided by 2. And the reason for all of that is just algebra. So that's just straight but tiresome algebraic manipulation. And now you bring out your womp stick and you say, hey, guess what? I just showed that the sum of the first n plus 1 integers is equal to n plus 2 times n plus 1 over 2. Well, that's what P of n plus 1 would say. P of n plus 1 says the sum from I equals 1 to n plus 1 is equal to n plus 1 times n plus 2 divided by 2, which is what I just showed. The sum from I equals 1 to n plus 1 is n plus 1 times n plus 2 over 2. Womp stick to womp the person reading the proof over the head with what you've, in your mind, made clear at this point, which is that P of n plus 1 is true. And the reason for that, definition of P of n plus 1, and step 5. Because we just proved this thing, which really is the definition of P of n plus 1. And now is the fun payoff, right? You've done the hard work, so collect your prize, right? Therefore, P of n implies P of n plus 1. Why do we know that? Because we started with P of n, and we ended up with P of n plus 1. So put that down as a separate statement. P of n implies P of n plus 1. We know that's true now. Well, why is that good news for us? That's good news because that's our inductive step, right? That's what we were trying to prove. Therefore, P of n for all n bigger than or equal to 1, and the reason for that is mathematical induction, and that's what we were trying to show. So we proved our base case, we proved our inductive step. That's why we can apply mathematical induction and say P of n for all n. So there's two parts here, right? The first is knowing the mechanics of doing a proof, which was an earlier topic in the course, this business of writing down step by step, explaining the reason and so on. And the second part is understanding how mathematical induction lets us do something like, prove this statement for all n by taking it and putting it into the form of a family of propositions, proving a base case, proving an inductive step. Yeah, you can write MI for short. So what I'm most concerned with in proof type questions is making sure that you're starting with what you know and then only writing down things that are true after that. What I don't want to see is, prove X. I don't want you to start with X and then show that something is true because of that. That's backwards. That's not a proof of X, right? If you want to prove that X is true, you have to start with something you already know is true, right? 1 plus 1 equals 2. And then you start arguing from there, and eventually you come down with X. Okay, that's a good proof of X. But if I say prove X, and your first statement is X, right? You don't have a reason for writing X. You don't know that X is true. So your whole proof is built on something that's unproven. Now the one difference is an indirect proof. When we say prove X, sometimes we'll assume not X and argue to a contradiction, a fallacy. And that will let us logically conclude X. So let me write that out. And this is earlier in the study guide anyway. So prove X, direct proof. So prove X. So you write something which is true, something which is true, something which is true, and you conclude X eventually. So this might be, some other hypothesis that you're given, or, the sun also rises, or some fact that to be true, and by applying different rules of logic and so on, if you can eventually prove that x is true, you're done. You've proven x. An indirect proof so we want to prove x. So we start off with not x. And this is the negation of whatever it is, the conclusion that you're trying to prove or whatever. And now you argue logically, and eventually you prove that false is true. That's a contradiction. And now you've proven if x is not true, then false is true. Right? In other words, if this is not provable, then false is true. Well, false can't be true. So x must itself be true. So that's a valid way to prove x. Okay, let me do not a proof. And this gets you the sad face. Okay, so don't do this. Prove x. X, blah, 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 true. That does not prove x. This only proves if x is true, then true is true. So you've proven true is true, which is good to know, but it doesn't prove x. If you start with something that's true, and you prove x depends on that, right? Then if true x, well, that proves x. If you start off with not x and you get false, well, that proves that x must be true. But if you start with x and you end up proving that something is true, that has nothing to do with whether or not x is true or false. And a classic example is, prove 1 plus 1 equals 3. So that's the x we're trying to prove. Well, if I start off my proof with 1 plus 1 equals 3, and then I multiply both sides by 0, and so this is 0 plus 0 equals 0, 0 equals 0, and that's true. Have I proven that 1 plus 1 equals 3? No. All I've proven is that if 1 plus 1 equals 3, then 0 equals 0. If I won the lottery this week, 0 is still equal to 0. That doesn't prove that I won the lottery. So make sure when you do these proofs, inductive proofs, non-inductive proofs, any of these proofs, make sure you're always going in the proper direction. You're either starting with something that you know is true and proving x, or you're starting with not x and proving a contradiction. All right? That's probably the most important thing about proofs. And, I'm hoping to see reasons for your steps and logical, movement from one step to another. And, names for these and so on and so forth. But as long as you're doing something in the spirit of writing this thing up formally, right, I'm probably going to be pretty happy. As long as it's a valid proof, too. All right, so that's induction, reasoning from what you know or assume. Those are your starting points. Let's see, what else? So that also covers this section on proofs, right? So direct or indirect contradiction proofs, working from what you know to what you don't. When it's all right to start with what you don't know, that's when you're proving by contradiction. We don't know that x is false, but we can assume x is false and then argue to a contradiction. All right, number theory. So, number theory, we didn't get through everything that I normally try to get through, but actually, some of the things we missed, like Euclid's algorithm for greatest common factor, we will cover in 223 because we'll use that in an early assignment. So we'll pick up some of these things next quarter. But for the exam, you should definitely understand divisibility, right? And remember the order of this symbology. So A, vertical bar B, this means A divides B. So for example, 3 divides 6. 6 does not divide 3. Right? So A divides B means B can be written as some integer multiple of A. And we're always talking about integers here, right? Obviously I can divide 3 by 6, I get 0.5, but that's not an integer. And then there's this question of congruence. So congruence is just remainder. So if we're working modulo 7, we're looking at remainders when you divide a number by 7. So what's left over after you divide by 7? So if I start with the number 12 and I divide by 7, 7 goes in once with 5 left over. So 7 is congruent to 5, or 12 is congruent to 5 modulo 7. And so we can take all of our infinite set of integers and we can reduce them to a few small integers based on their congruence modulo some number. And then we can do things like arithmetic on these numbers. And we can do this reduction modulo something either before or after or during our calculations. So if I know that 12 is congruent to 5 modulo 7, I automatically know that 144 is congruent to 25, which is 4 modulo 7, right? Because I can square both sides and they'll end up still being congruent to each other. But I could also take 144 and divide by 7 and see what I end up with. And I'm going to get, 144 is 20 times 7 plus 4 left over. So the whole point of working in modular systems is that we can take problems about potentially large integers and reduce them to operations on smaller integers by using this modular equivalence. And there's always a unique number that we can reduce an integer to, and it's unique in the sense that it's not negative and it's less than the modulus. And there's always a number and it's unique, and that fact is called a division algorithm. Prime numbers, we know what a prime is. It's a number that's not divisible by anything except itself and 1. It's got to be a positive integer bigger than or equal to 2 in order to be prime. We have a fundamental theorem which says we can break any number into a unique product of primes. So 1001 is 7 times 11 times 13, and there's no other way to factor 1001 into prime numbers. And then we talked about modular exponentiation, which again is using this idea that we can reduce modulo something at any point that we like. So 12 to the 97th modulo 11. Well, I could multiply 12 by itself 97 times and then divide by 11 and see what the remainder is. But I can also say that since 12 is congruent to 1 modulo 11, 12 to the 97th is the same as 1 to the 97th, which is just 1. So with doing almost no work, I know that this is going to be 1 more than a multiple of 11. So doing those kinds of tricks, we can do a lot of manipulation of large numbers without too much work. So modular exponentiation is a particular example of that. And it's a technique that works like this. let's say I wanted to do 12 to the 97, and it didn't happen to turn out that, 12 is one more than 97. Here's what I can, well, no, that's going to be too easy an example. Let's do this modulo, let's do this modulo 5. So here's what we do. We say 12 to the first is 12, which is congruent to 2 modulo 5. 12 squared is going to be congruent to 2 squared, which is just 4. 12 to the fourth will be congruent to 4 to the, sorry, 12 to the fourth will be 12 squared squared. And since 12 squared is congruent to 4, this is congruent to 4 squared, which is 16, which is congruent to 1. 12 to the eighth will be congruent to 12 to the fourth squared, which is 1 squared, which is 1. And you can see a pattern now, and you usually get a pattern developing pretty early. 12 to the 16th is congruent to 1, which will also be 12 to the 32nd, which will be 12 to the 64th. All right, so once you've calculated 12 raised to different powers of 2, now we go ahead and we break 97 into binary. So 97 is equal to 64 plus 33, so plus 32 plus 1. And so 12 to the 97th will be 12 to the 64 plus 32 plus 1. And law of exponents says this will be 12 to the 64th times 12 to the 32nd times 12 to the first. And we've calculated what each of these is over here in our calculation on the side. So 12 to the 64th was 1, 12 to the 32nd was 1, and 12 to the first was 2. So this whole thing is congruent to 2 modulo 5. So that's modular exponentiation. And I think you did one of these on homework. And it's one of these tricks. There's some other tricks we can do along this line that we didn't go over. The main one being Fermat's little theorem. So that won't show up on the exam. But there are other things we can do along these lines. Let's see. That's pretty much it for number theory. We did not get into any applications this quarter, unfortunately. But we may find a way to talk about those in 223. Well, I mean, we've talked about hashes in 222, and that's one application of some of this stuff. But maybe we'll do some coding theory in 223, and that'll get us into some crypto or something. So we'll see. Propositional logic. So that's kind of the foundation for all of the proof stuff that we're doing. So the building blocks of these propositional statements: conjunction, which is an and; disjunction, which is an or; implication, which is an if-then. No coding questions on the exam. So code-free zone. Implications, rules of inference, right? So direct reasoning, detachment, right? Indirect reasoning, so on and so forth. So page 57 and 58 in your text, definitely, put that in your notes. Those will be handy when you're writing out proofs and you're trying to find reasons for things. Keep those bookmarked or printed out. It'll definitely be useful. Logical equivalence, so two things are logically equivalent if they have the same truth value in all possible situations. And if you look in terms of truth tables, it means that every row of the truth table is exactly the same value for both expressions. That's how you know two things are logically equivalent. Quantifiers, so for all and there exists. So these funny symbols. For all x, something is true, or there exists an x such that something is true. And we've played around with these. We did some word problems. We put these together and so on and so forth. So universal quantifier says this is true for every possible value of x in the universe. Existential quantifier says this is true for at least some particular value of x. And we can modify this with an exclamation mark. This says this is true for exactly one unique value of x. So there exists a unique. Fallacies, two main fallacies we worked with. Fallacy of denying the conclusion or affirming the hypothesis. And so these are things that are not guaranteed to be true. So P implies Q, Q for Q, therefore P. So this is affirming the conclusion, right? If I win the lottery, then my hair will be brown. My hair is brown, therefore I won the lottery. Doesn't work. And denying the hypothesis also does not work. If I win the lottery, my hair is brown. I did not win the lottery, therefore my hair is not brown. Does not work. So those are fallacies, and they're kind of the flip side of the valid laws of reason that we call detachment and indirect reasoning. So you should know those two fallacies. And then we're back to our first week when we did set theory. So, summations, nested summations, the little product symbol, the uppercase pi, right? Which is like sums, but you multiply. Matrices, I'm not going to ask you anything on matrices. Functions, so functions are maps from one set to another. Three categories: injective, which means different things map to different things, right? You can't have two things over here mapping to the same thing. If everything maps to different things, that's injective. Surjective says everything over here gets mapped to from something over here, so it's sometimes called an onto function. It means everything here comes from somewhere. Bijective means it's both injective and surjective. Domain is where you're mapping from. Codomain is what you're mapping to. Range is the set of values that you map to. Requirements to be well defined, so that's called the vertical line test in math courses. But basically, this function has to map to one thing over here. It can't map to two things. If it maps to more than one thing, it's not a well-defined function. So f of x can't be both 5 and 7. F's not a good function if that's the case. And then set theory, the beginning of it all. So operations on sets, so unions, intersections, complements. Don't get tripped up on complement operation. Remember, if we have two sets, A backslash B or A minus B equals the set of all things that are in A such that they're not in B. So you start with A and you throw away anything that you find in B. Right, so it's subtracting this out of A. And if you see this uppercase C, so B raised to the C, that's the complement of B. And that's really the universe take away B. So it's everything that's in the universe but not in B. And we've played with Venn diagrams. So if this is A and this is B, then this is A take away B. And if this is the universe and this is B, then the complement of B is basically everything that's in the universe but not in B, which is just the stuff outside B. You can't usually prove things with Venn diagrams, right? If I ask you to prove some fact about sets, this will not constitute a proof. You can do this maybe to demonstrate, but it's not a valid proof, right? Because what if B was, wide and skinny, right? How do I know that this picture would still show this thing? So these are, illustrations of statements about sets, but not proofs. So complements in the universe, standard sets, integers, rationals, reals, subsets and power sets. We started off talking about those. Cartesian products, where you take all the, Cartesian product of two sets are a set of tuples, where the first element of the tuple comes from the first set, second comes from the second set. We've got examples from homeworks and such on that. And set identities, so these correspond to Boolean identities from 250, logical identities from when we talked about propositional logic and so on. So, A union B equals B union A. Or, the complement of A union B is complement A intersect complement B, De Morgan's theorem, and so on. And we can prove properties about sets by using things like membership tables, which are basically truth tables. And we can make a membership table for two expressions if they're always equal for all possible values of the sets. Then we can say these two expressions are the same. There you go. That's the whole course in an hour and 20 minutes. So I guess we didn't need 10 weeks. We could have done it in 80 minutes. That's pretty much all of 215 that we've done. So final exam will be similar to the homework, similar to the midterm. So go through those. Definitely recommend, if you're trying to do extra prep for this, go through the problems in the book. There's an extra textbook that has some of the number theory stuff in it. Just practice doing some of those problems. If you can do the problems that were on homework, if you can do the problems from the midterm, you're probably in good shape for the final, okay? Don't stress over this, okay? If there's something that you don't understand anything about, okay, stress a little. Go back and try to pick it up, right? Go through the lectures, the books, work out problems. But if you can do the problems, if you understand what you were doing on the assignments and so on, if you've looked at my feedback on your homeworks, right, and that's important, then you should be in good shape. But again, there's cases where you might have gotten full credit on the homework, but I saw some things that were concerning, in which case I posted comments in the homework. So make sure you always look at those, because I might say, hey, I've got, a sense you understand the basic concept here, but make sure you do such and such. And if you don't do that such and such on the exam, you might lose points there. All right, cool. We are out of time. We are out of 215. So I will see you Wednesday for your final here. I'll see you Monday if you're in 222. Thank you so much for the quarter. It's been fun for me. I appreciate all of the input and energy from everybody in the class. Have a great weekend, and I will see you next week. You're welcome. Yeah.